Well, hello and welcome you to Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are dealing with section 4.6 in Big Ideas Math for the Integrated Math 2 textbook. This is on complex numbers. Now, the first 5 sections that we did in chapter 4 were dealing with simplifying radicals, something we're still going to have to do. I don't think there's graphing in this, which I'm kind of happy about, but there are things related to the graphing section. But, solving by graphing, and then we solved using square roots, completing the square and quadratic formula, all of which we are going to be able to do with the concepts involved with what are called complex numbers. Because we've talked about this thing regarding no real solution. Well, there are some things that are called complex solutions, also known as imaginary solutions, and I hope that the book goes in detail about what imaginary numbers are, because I haven't read it, but I hope they go into detail what imaginary numbers are, how they're used in real life application, because I don't know fully every single bit of application. I hope they use word problems for it, and yeah, kind of like that. Now 4.6 is the thing just on complex numbers. It's the introduction of it, so we'll see to what extent they go. 4.7, I believe, is where we start solving those quadratic equations with complex numbers involved. So, welcome to the world of I. Not me, not the pronoun, not me. Welcome to the world of the letter I in math. It's not a variable. It's not a variable. It is a component for imaginary numbers or complex numbers. So, let's dive into the lecture portion of this thing, shall we? Where we are going to straight up define and use the imaginary number or imaginary unit I. Add or subtract complex numbers. This will be the easiest thing you can do. Multiply complex numbers is the second easiest thing you can do. A lot of these, I may not be a variable in and of itself, but for the most part, it's treated like variables do, with one little exception when you start doing the multiplication. You'll see what that's like. Here are some new phrases we're going to be talking about today. Imagine the imaginary unit I, just using the letter I. A complex number, which again, hopefully we get to define that in total. The imaginary number, okay. A pure imaginary number. I have to see what that difference is. I believe I am aware. And complex conjugate. Okay, we're going to get into complex conjugates as well. So I think I understand where they're going to go with the questions more so here versus what they'll do in section 4.7. And yep, just be ready for both sections working in tandem with each other very strongly. All right, the imaginary unit I. Hey, y'all. I just said this. Not all quadratic equations have real number solutions. For example, x squared equals negative 3 has no real number solutions because the square of any real number is never a negative number. Remember, you take the square root of both sides and you go to the calculator. What's the square root of negative 3? And it says domain error or something like that, or it says you can't do it. And then we just say no real solution. It's not no solution, though. To overcome this problem, mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equals the square root of negative 1. So taking the square root of a negative number translates to a component called I. Now, if you square both sides of this thing, squared and squared, then I squared becomes negative 1. Note that we're not squaring negative 1, guys. We are squaring the square root of negative 1. The square cancels out the square root, and then you're left with just the negative 1 in and of itself. So they do dive into that. We obviously, we are going to have to use that when multiplying complex numbers, and this is the wrinkle. Instead of like how x times x is x squared, I times I, being I squared, actually translates to negative 1. I guess something we'll get into, right? The imaginary unit I can be used to write the square root of any negative number. So the one thing I want to mention that I don't know if the book will, and I just want to bring it up right now before moving forward. It's very hard to talk to students. This might be you listening to this. It's very hard to talk to students about imaginary numbers and make them believe that there is a use, effect, or some sort of tandem. Students sometimes want to come up with a reason, like, where am I going to use this in real life or whatever else, which, this actually does have real life usage. But furthermore, what is the purpose if it doesn't exist? And guys, here's where I have to hit this home right now. Imaginary numbers are just as real as real numbers. I'm going to say that again. Imaginary numbers are just as real as real numbers. So, now there's this name, imaginary numbers, and you're also going to hear about complex numbers, which actually is a bigger umbrella term for all numbers. But, so if you ever hear me say complex, maybe that helps you more instead of hearing imaginary. But people then ask, well, then why do they call them imaginary numbers? That's a good question. I don't know. So real and imaginary numbers aren't any more made up than real numbers are, right? They're all kind of a created thing, within language or within our, system and things. But imaginary numbers are very real. Okay, I just want to make sure that makes sense. So if you're going to deflect on why do I have to use this if it doesn't exist, if it's not important, if it's not real, it does exist. It is important. It is real. So just, I don't know if that just, I'm not going to answer the full thing on that, but let's just not deflect on that. I just want to make sure you're very aware of that. Okay. Anyway, let's move forward. The square root of a negative number. If r is a positive real number, then the square root of negative r equals I times the square root of r. For example, the square root of negative 3 equals I times the square root of 3. Let's make sense of that a little more so. Let's use the negative 3 example. Square root of negative 3 is also the square root of negative 1 times 3, which can split up into the square root of negative 1 times the square root of 3, and the square root of negative 1 is I. So that's why it becomes I times the square root of 3, or as we'd say, I root 3. I root 3. So, when it comes to us solving quadratic equations in the future, involving complex numbers, they're no different than what we did before. We just throw in the letter I. I'm just going to say that right now. We just throw in the letter I. So, as far as solving stuff, we're going to find those solutions of those no real solutions, but to imaginary solutions, to complex solutions. We'll do those in 4.7, probably more so. Finding square roots of negative numbers. Excuse me. Again, more of that breakdown. This will apply when we actually solve for them. The square root of negative 25. Well, hey guys, what's the square root? Oh, here's where they do it. Where's the square root of 25? Well, it's 5. So this is square root of negative 25 is 5i. 5 times I, right? Square root of negative 72, you take the square root of 72, which breaks up into root 36 times root 2, or 6 root 2. The square root of negative 1 is I, so it becomes 6i root 2. Now I is the thing that pulls out of the radical, right? It's outside of it in this sense. So instead of the answer being 6 root 2 here, 6i root 2, and so on and so forth. We keep working that thing out. Negative 5 times root negative 9. Root 9 is 3. 3 times 5 is negative 5 is negative 15, and times the I is negative 15i. So here's another thing I want to mention, guys. Square roots of negative numbers aren't necessarily negative numbers, right? 5i, it's a positive it's a positive imaginary number. And then negative 5 times root negative 9 is a negative imaginary number. So square root of a negative is not a negative number, it's an imaginary number. Just like raising to a negative exponent isn't a negative number, it's dividing by something. Here are some more examples, and we'll keep moving forward. All right, let's dive into the complex number, just the phrase in and of itself. A complex number, written in standard form, is a number a plus bi, where a and b are real numbers. The number a is the real part, the number bi is the imaginary part. Okay, now that might sound a little strange to you as far as what this whole thing is. Hey guys, you know what a complex number is? Any number you've ever seen in existence. Any number you've ever seen in existence. We used to think of those as real numbers before a few minutes ago. Negative 1 is a complex number. 5/3 is a complex number. Pi is a complex number. Root 2 is a complex number. See, these are rational. These are irrational. All of these are real, but they also all fit under the complex numbers umbrella. But you know what else are complex numbers? Imaginary numbers. So that's why I say any number you've seen in existence. Now that we've seen I root 3, now that we've seen 5i and negative 15i, you've now seen complex numbers in their entirety. Every number we've seen, and that includes when you combine, not like combine like terms, but when you combine forces, a real part to an imaginary part, a real number and imaginary number added together or subtracted or what have you, those fit just under the complex number umbrella. There's a real part, there's an imaginary part, added together we get the complex part. So I guess here's where, here's the pure imaginary versus imaginary. So imaginary numbers in the a plus bi format, we call those imaginary because they have an imaginary component. When the real component is 0, then they're known as pure imaginary numbers. Nothing else but the imaginary number in and of itself. So we can call these imaginary or complex. We can call anything complex. We can call these real or complex, and you are good to go, my friend. You are good to go. So, that's what we got. I should probably be moving faster now. Two complex numbers, a plus bi and c plus di, are equal if and only if a equals c and b equals d. Great. Find the value. Okay, well, we're going to have some examples of it. So find the values of x and y that satisfy the equation. 2x minus 7i equals 10 plus yi. So really what you have to do is divide these into parts. get the real number component 2x and 10 together in their own equation. 2x equals 10, therefore x equals 5. You can only have the real thing meant to the real part, and then the imaginary thing meant to the imaginary part. Negative 7i equals yi, and solve then for y in that scenario as well. You divide both sides by I, basically. Negative 7i equals what I? Negative 7. So great, we'll do some examples of that. It's a very straightforward process, just to make sure that you are hitting home what a complex number entails. Adding and subtracting complex numbers, guys, it's just as straightforward as combining like terms. I'm just going to say that right now. They're probably talking about it. Add the real parts and imaginary parts separately. To me, it's just any terms that have I in it can add together. 2i plus 5i is 7i, just like 2x plus 5x is 7x. And 2 plus 5i do not combine to become anything, just like 2 plus 5x do not combine to become anything. The difference is when we write something in standard form of an imaginary number, of a complex number here, the I term goes last. We write it as a plus bi, that variable. Instead of how we generally write an x term first and a constant second, the real will go first, the imaginary will go second. Now, they're going to write it probably in a different looking format where we add the, I'm just going to look to combine like terms, guys. I'm going to look to combine like terms. But add or subtract these, 8 minus I plus 5 plus 4i. You add 8 with 5. This isn't FOIL, by the way. That's a plus. So you add 8 with 5 to get 13. And then you do negative 1i plus 4i, which is 3i. You get 13 plus 3i as your new complex number result. That's their standard form equivalent. The next one here, 7i minus 6i minus 3 minus 6i. Now, for me personally, I like to distribute that negative, So we're going to do 7 minus 3, boom. And then negative 6i minus is minus negative is a plus. Negative 6i plus 6i, which is 0i. 4 plus 0i also means 4, just like 4 plus 0x would just mean 4, which means this is just a real number. Strictly just a real number. There's no imaginary component when you add the two complex numbers together. They cancel each other out. And lastly, we have this one here, distribute. So I'm big on, again, distributing the negative. I'd work more in that format. I got 13 minus 2, which is 11. And then distribute the negative. Negative 7i plus 5i is negative 2i. So we got that there. Hopefully that's making sense there. It's really just a combined like terms thing. All right, solving a real-life problem. Where are imaginary numbers used in real life? Well, here's an example. Electrical circuit components such as resistors, inductors, and capacitors, if I said capacitors, sorry, all oppose the flow of current. This opposition is called resistance for resistors and reactance for inductors and capacitors. Things I'm relearning. I have not seen this in like 20 years. Not 20, 15 maybe. Each of these quantities is measured in ohms. The symbol is used for ohms is omega, the uppercase Greek letter omega. Okay, well, there it is. Component and symbol. So for a resistor, resistance or reactance in ohms, we use R, and impedance in ohms, we use R. I actually want to know what to do with this problem. I don't know what we're going to do with the problem. Inductor, we use L for resistance, reactance. For impedance, we use Li. So there's an imaginary component for the inductor portion, which you see that symbol. I might have to go back to this example, not just for you, but for me. I might have to go back to the example for the actual figures if they don't show them for me later. Capacitor uses this guy right here. There's the capacitor. It has two parts. Resistance, reactance is C, and the impedance is negative Ci. This isn't stuff I'm going to remember. That's a for sure. This table shows the relationship between a component's resistance or reactance and its contribution to impedance. A series circuit is also shown with right now I'm just reading. I'm taking things in. A series circuit is also shown with resistance or reactance of each component labeled. So we have all the labeled parts of what is inductor versus capacitor, etc. The impedance for a series of a circuit is the sum of the impedances for the individual components. Find the impedance of the circuit. Okay, let's let an example lead us in this because I'm not an electrical engineer. I don't work this stuff specifically. The resistor has a resistance of 5 ohms. So we see here, resistor with this symbol. They use 5 ohms for it. So its impedance is 5 ohms. If the resistance is 5 ohms, the impedance is therefore 5 ohms. Boom. The translation is straight up 5 is 5. Okay. The inductor has a reactance of 3 ohms. So whatever that number is, this guy, inductor, reactance of 3 ohms, its impedance is 3i. ohms. So we're trying to come up with the impedance of the circuit, and it's a translation from whatever the resistance or reactance is. I don't know if the two words, I'm just going to keep saying resistance, I guess. Do they say different things? Oh, inductor has reactance, resistor has resistance. Okay. The capacitor is a reactance of 4 ohms. Boom. So its impedance is negative 4i ohms. If I have a 4 here, this becomes negative 4i. What we're going to do is combine the results of these things here. Now, if there's one thing that I do know, and we're probably going to take it into effect, this is going to be a long lecture portion. One thing I'm going to take into effect probably later with this stuff is where imaginary numbers exist on a number line. Because we have a real number line that, goes this way. Just, the number line, here's 1, 2, 3, 4, 5, and -1, -2, etc. They go this way. That's the real axis. The imaginary axis goes this way. It's perpendicular to it. And there's something that has to do with, literally, if I don't want to use all the things if they don't use them all, but there's an actual directional component, like that north-south aspect that has to do with this, being perpendicular to the real axis that has something to do with it. So when we're seeing the resistor going left-right or parallel to its alternating current source right here, that left-right bit, that is part of that resistor component being real. And then the perpendicular portions being imaginary has to do with this. And it probably has to do with the flow of this current itself. So with the, what was this, the inductor? The flow of current probably goes this way. It goes upward, positive, with the I component this way. This is one way I'll remember it. I just got to know the symbols. This is the inductor. And then it flows this way, positive, right here for that. That's why that stays positive. And when this goes down here, the I components go up and down, but when it goes down, it's negative. And it goes back to there to finish the circuit, to complete the circuit. So there's one version of that the I component changes the direction of these things and lets the flow go north-south or just perpendicular to the real version of it, where you can then determine the impedance of the overall circuit this way by adding these together. What is, and there's nothing on this side, but what is 3i plus 5 plus negative 4i? 3i plus 5 plus negative 4i. So 3i minus 4i is negative I, and that's where they combine. You get 5 minus I. That's the impedance of the circuit. It's actually literally using this stuff. Again, what we use I for, it's the I itself is just a component to indicate how far in these directions that we're doing things, at least with regard to this. Square root of -1 or not, applied. There are rules within it, and I think I'm arguing more logic than anything else. I'm trying to give you the why for something that I'm not fully vested in, but I'm enough to say it matters. It's enough to say it matters. So that's an answer. Whether or not you use it in your life, I haven't used it in my life. Whether you use it in your life or not is going to be a totally different story. Okay, I'm going to move forward. Add and subtract, they do some more examples of that kind of stuff. We'll get into them when we do the assignment. Multiplying complex numbers. Hey guys, this is going to be just like you do any other multiplying things. The one difference, I'm just going to say it right now, the one difference is that when you get I squared, we turn I squared into -1, which means when you multiply an I with an I, you are actually getting a real number out. An imaginary number, a pure imaginary number times a pure imaginary number is actually a real number. So A plus BI times C plus DI, they're showing a concept here where you basically FOIL. You're doing first times outside times inside times last. And I think we best see it in this line right here. In this line, let's go back. In this line right here, where we go A times C, boom. A times DI, boom. BI times C, boom. Remember, B and C are the number portions of it, times the I imaginary component. And BI times DI, B times D, boom. I times I is I squared. But check it out. I squared is -1. And -1 times BD means negative BD, which means it gets to subtract with the AC. So they are doing it this way to mesh and show you here that there's the real component here and the imaginary component here. And then you're left with the things. This doesn't have numbers on them. We'll obviously do an example. And look, they talk about FOIL right there. We'll get to it. How they write the example might be different than how I actually do it. And that depends on if you're doing binomial times binomial. Here's a monomial times binomial with an imaginary part. 4i times -6 is -24i. 4i times I is 4i squared. I squared is -1, so that'll translate into -4. And remember, when I'm doing the lecture here first, that means when I do these problems, I'm not going to do this step. I'm going to go straight to this step. 4i squared is negative 4. Boom, because it multiplies by negative 1. I might say it out loud, but I'll probably skip that step outright. We'll see. Be sure to simplify I squared as negative 1, because there should only be 2 parts to that. Boom. And notice they wrote the real part first, the imaginary part second. This next one is straight up FOIL. 9 times negative 4 is negative 36. 9 times 7i is 63i. Negative 2i times negative 4 is positive 8i. And negative 2i times positive 7i is negative 14i squared. I times I being I squared. I squared is negative 1, and subtracting a negative means addition. So it becomes a real number. We do negative 36 plus 14 to get negative 22, and 63i plus 8i combines to become 71i. Here's the results of multiplying those things. I got to figure out if multiplying them is something that occurs in engineering, but more so it'll happen when we deal with what are called conjugate pairs, so we know how those things work. Hopefully that comes up soon. Oh, that's coming up right here. So we're skipping this guy right here. All right, pairs of complex numbers of the forms a plus bi and a minus bi, where b doesn't equal 0, are called complex conjugates. Now, we've dealt with conjugates in the past when it came to rationalizing the denominator. If you recall, we had some a plus square root of b, so we'd multiply by some a minus the square root of b, because this becomes a difference of 2 squares, which cancels everything out. Imaginary numbers also have complex pairs, a plus bi and a minus bi. If you can see what happens here, the result is, again, difference of 2 squares. It becomes a squared minus b squared I squared. You square this part, or bi quantity squared. But because I squared is negative 1, this becomes addition, a squared plus b squared. Yes, there is something called the sum of 2 squares, but it doesn't factor into real components. There's an imaginary component. In order to get the middle terms to cancel and everything to be positive, you need an imaginary number for it to happen. And that does make it a real number, which means rationalizing a denominator, making it real, is going to be multiplying something by its conjugate. And obviously that's something we got to get into in a bit. Okay, multiply 5 plus 2i by its complex conjugate. 5 plus 2i's complex conjugate is 5 minus 2i. So in multiplying those bits, the middle terms cancel. And then you're left with 25 squared minus 4i squared. I squared is negative 1, so you get 25 plus 4, which is 29. You know, I'm probably just going to go straight into it like this. Because it's a squared plus b squared. 5 plus 2i times 5 minus 2i is 5 squared minus negative 2i squared, or negative 4i squared, or 5 squared plus 2 squared. The I is gone because I squared is negative 1. Some examples down below. Okay, and that is it for those parts. Now that we've closed off the lecture, let's jump into the vocabulary and core concept check before doing problems 5 to 74 on this thing later. Okay, so let's go and take a look at what's going on. What is the imaginary unit I defined as, and how can you use I? I is, oh, that's not writing. Oh, I just lost my mouse portion. Hold on. I have no idea where it just went. I represents the square root of negative 1. I is the square root of negative 1. That's what it's defined as. How can you use I? It's used to I take square roots of negatives. Used to take square roots of negatives. I'm trying to think if they want more. Obviously, we're doing more things with it. There's things with the engineering and electrical circuits. Square roots of negatives. To find and find non-real solutions. I'll say that. Non-real solutions, which is more important for the next section, to quadratic equations. Normally I type this stuff out, but they gave me a little bit of room. All right, for the complex number 5 plus 2i, the imaginary part is 2, and the 2i, and the real part is 5. Actually, let me double back on that and confirm that we say, because it might just be 2. The I is the component that multiplies by that. Let me just be certain one way or the other. I think I have to erase that after. Bi is the imaginary part. Okay, so yeah, 2i. 2i is the imaginary part and 5 is the real part. Describe how to add complex numbers. I'm going to say this straight up, y'all. Combine like terms. Combine like terms. Which means add imaginary with imaginary and real with real. Real with real. Imaginary with imaginary. Okay. Last one. Which number does not belong with the other 3? Explain your reasoning. I got 3 plus 0i, which is known as a real number because the 0 part is not there. Let's call that A. This is a whole complex. Now, listen, all these are complex numbers. Actually, you know what? I'll just put this. They're all complex numbers. These ones are imaginary numbers, though. 2 plus 5i, because it has the imaginary component. That's an imaginary number. I'll call that b. I'm sure that's different. Root 3 plus 6i, although that's irrational, that has no bearing on whether it's real or imaginary. This is also imaginary with a real component. That is b. And this is a pure imaginary number without the real. It's also imaginary, but pure. I'm going to go ahead and assume that because that has an imaginary component, it's also b. A is the different one. This is strictly a real number as 3. These are new numbers you hadn't seen before, I assume. And those have imaginary components that make them imaginary numbers, although this one is pure. And that's where I'm going with that. Okay, guys, we are going to go ahead and move forward to the problem set where we have numbers 5 through 74 to do. It looks like it can end up being a pretty good drill and kill. I'm kind of excited about that. If you, and I'm just going to say it right now, if you listened to the lecture portion of this, then you're probably better off when it comes to me being faster with it. If not, you might want to listen to some of it. I know it was 22 minutes long. I recognize that, but you know, this is part of why I include it. I include it so you can hear something before we hit the drill and kill here. So we'll go straight into this problem set where we hit numbers 5 to 74. Excuse me. Okay. In exercises 5 through 12, find the square root of the number. So on number 5, again, I'll dive faster into it over time. But the square root of negative 36, it's the same thing as the square root of 36, guys. The difference is you're going to be multiplying this by the square root of negative 1 as well. The square root of 36 times the square root of negative 1 split up. Square root of 36 is 6. Square root of negative 1 is I. You're left with 6i. Now, I'm not going to be writing that in between step here on out. If I have a negative inside my square root, which every problem here does, then an I comes out of it. I will write a second version of this next step here because it's going to have to apply to future problems. So check this out instead. Number 6. The square root of negative 64 is the same thing as I times the square root of 64, if that makes sense. Now it's a positive inside the square root. What's the square root of 64? Well, it's 8, so it becomes 8i. And so you can tell like where that kind of comes to be and how I would multiply it in front if, say, I couldn't simplify the inside, but I totally could. Everything comes out as a result, and that's what we get. Number 7, the square root of negative 18. Now, this one probably is better off for me to actually write this first, the I root 18, because it really talks about, I got to simplify this thing. It's not a perfect square. Not everything's going to come out, but some things are. Now, we've been simplifying radicals all chapter, from section 4.1 onward. So the square root of 18 is root 9 times root 2, or 3 root 2. So how do I do I times 3 root 2? I'll put the 3 before the I, multiple, kind of like 3x. So it'll become 3i root 2. 3i root 2. That's the way that it's written. So what's the difference between square root of negative 18 and square root of 18? There's an I in it. I mean, all these. What's the difference between this and the other? There's an I in it. What does the I do? It makes it an imaginary number. I mean, that's all we're going to say about it. But yeah, there's an I in it. So there's nothing different about what we're doing with these versus what we had done in the past, especially when we solve quadratic equations next, which is hopefully going to be very familiar, very comfortable, especially after doing this section. So square root of negative 24. Let's see if we can do this one in one step this time. Oh, well, after the I root 24. Next time I'll do as few steps as I can. Root 24 is root 4 times root 6, or 2 root 6. So this becomes 2i root 6. Like so. Now, numbers 9 through 12, you can see there's a number in front, which means I will have to kind of write a second step, or I think it's worthwhile to write the second step in between, even if I simplify the other part kind of fast, like this. 2 times the square root of negative 16. Square root of 16 is 4, so square root of negative 16 is 4i. We'll do 2 times 4i, which is 8i. So I am writing the in-between step, and generally I don't write these things left to right, but I really want to see a full snapshot of these. So that becomes 8i, like so. See, this is pretty drill and kill, this part right here. A lot of them I think will be, because a lot of these are based off little algebra things you know, or things previously from the chapter. Very easy parts. Easy parts. Negative 3 times root negative 49. And I mentioned this in the lecture portion, by the way. Square roots of negatives don't mean negative numbers. You can tell none of these were negative. They're positive. They're imaginary, but they're positive. Here's where we're going to actually deal with a negative, because we're going to multiply an imaginary positive by a negative. So, we're finally going to get a negative number out. This becomes negative 3 times 7i, square root of 49 being 7, and the negative being inside there. So we'll get negative 21i, an imaginary negative number or a negative imaginary number. Number 11, same thing. We're going to have another negative imaginary number. Negative 4 times square root of negative 32. But on these two, we're going to simplify this other radical. So this is going to be negative 4 times, well, 32 is root 16 times root 2. So 4 root 2. Or in this case, 4i root 2. Yeah. Negative 4 multiplies with this 4, being real components to numbers there. Negative 4 times 4 is negative 16. So this will be negative 16i root 2. And then lastly, number 12. 6 times negative root, 6 root negative 63. That'll be 6 times 63's largest perfect square is 9. So root 9 times root 7 is 3 root 7. So 6 times 3i root 7. This will be a positive imaginary number. 6 times 3 is 18. We get 18i root 7. So, once again, if that went too fast, you're going, well, wait, how'd you get this number? How'd you do it? Well, you have to go to section 4.1 or any of the previous ones, 4.3 even, whatever, where we've been simplifying radicals. So I hope you've been good at simplifying radicals in the past. It carries forward to this set. All right, numbers 13 to 20, we're going to find the values of x and y that satisfy the equation. So in this case, so 4x plus 2i equals 8 plus yi. In these cases, and these problems are going to start to sound really redundant. I think there's probably a time where maybe we can, we have some fractions, but maybe there's a part where we can skip what we write for work if we're pretty good at it. I don't think I will. But we're going to split into two parts, right? The things with i's are imaginary parts. Things. And so imaginaries can only go with imaginaries, meaning I'm going to write an equation given these two things that make 2i equal to yi. If these are going to be equal as far as a number goes, because a complex number is two parts, then I need 2i to equal yi. And if I not really divide both sides by y, but if I look introspectively at just the 2 and the y right here, I need 2 to equal y. I need y to equal 2. Y needs to equal 2 in that case with the imaginary parts. 4x and 8 being a real number, I need to find an x value that will give me 8 when multiplied by 4. Divide both sides by 4, you get x equals 2. So that's where we're solving that thing, right? Those things. That's where that makes sense with what we got. Just put the separate parts equal to each other, imaginary part and real part, and solve. And that's where, maybe there's a way that we can kind of work a little faster, all depending. It's just one more step otherwise. But number 14, 3x plus 6i equals 27 plus yi. I don't know how confusing some of these problems will go. Let's do the real part here. 3x equals 27. So x equals 9. Yeah, I'm fine writing that step. That doesn't matter. So 9 is the value that's going to make that work. And by the way, I should also write out what these complex numbers are in full afterwards so you're not confused as to what we're doing. I'll do that in a bit. 6i equals yi. That must mean that y has to equal 6, right, as a result of that. So just so you're aware, on number 13, the full complex number would have been obviously 8, because x is 2. 8 plus, and then the y being 2 is 2i. So 8 plus 2i, that's not the answer, but 8 plus 2i is the complex number that we're talking about in full. And in this case here, this will be 27 plus 6i. Right, let me keep those up. 8 plus 2i and 27 plus 6i. And that's kind of what we're dealing with in the end when you have both x and y involved in the end. Number 15. Negative 10x plus 12i. They have a lot of problems for these that seem very samey in what we're doing. Plus 3yi. Okay. So negative 10x plus 12i equals 20 plus 3yi. We're going to set the x's equal, the real number parts equal. Negative 10x equals 20. X would be negative 2. And then here in blue, we got 12i equal to 3yi. So once again, kind of just divide the i's if you need to. The i's aren't really a part of what I'm looking at. I'm really just looking at these guys here. 3y equals 12, so y equals 4. I think if they're going to keep, I'll just keep doing that there. So that whole real number bit, I guess, is 20 plus 12i, right? I'm looking for the parts that don't have the variables and putting them together. When x is negative 2 and y equals 4, that's what makes those things equal to that complex number. Right? What makes the left side equal the right side? Number 16. 9x minus 18i equals negative 36 plus 6y once again, not once again, but notice how the I is coming after even the variable in this case, because the x or the y are part of real numbers, so the imaginary part comes after the fact. It's not an alphabetical thing this time. I is not a variable, but there are a lot of things like variables that we treat it as because you're multiplying it with another number to do something. And just like anything else, where we would combine like terms in that way. 9x equals negative 36 and divide both sides by 9. You get x equals negative 4. And then negative 18i equals 6yi. Just ignore the i's here, where we get 6y is negative 18. Divide both sides by 6, you get y equals negative 3. So it looks like that result of those two the complex numbers, negative 36 minus 18i. Boom. Boom, skis. Number 17. We have 2x minus yi equals 14 plus 12i. We're going to set 2x equal to 14. Divided by 2x is 7. We'll set negative yi equal to 12i. So negative y is 12, therefore y is negative 12. That full result is 14. Oh, well, it's 14 plus 2i, right? 14 plus 2i is the number. I like this one kind of more as far as the question. Hey, what value of x gives me, because this is the actual complex number. I need the x and y that makes me this complex number. Instead of interchangeably working it, I don't know why they didn't do these. I feel like these are the more natural versions of the problems that you'd probably want to begin with anyway. Number 18 looks like the same thing. X and y on the same side of the equation. Negative 12 plus yi equals 60 minus 13i. For the real portion of this, we're going to set negative 12x equal to 60. Divided by negative 12, you get negative 5 for x. And for the imaginary portion, we want yi to equal negative 13i. Therefore, y would be negative 13. Yeah, we got it. Number 19. Got some fractions. X and y are not only on opposite sides of the equation, but they're switched from where they were to begin with. Now the real number is plain in sight on the left side, and the imaginary is plain in sight on the right side. We didn't have that before. Okay, so we have 9x minus 4i. No change in what I would do for this thing. 54 is 9x. Divide both sides by 9. We'll still get 6 for x. For the y portion, we're going to set negative 1/7 yi equal to negative 4i. Now, let's drop the i's for a moment. Let's even drop the negatives. Negative divided by negatives are positive. So we get 1/7 times y equals 4. That's what we're doing. We're going to multiply both sides by 7. I'll just write that out. Times 7 times 7. Because 7 over 7 is 1, and we're left with y equals 28. That's the value that would get us there. And the complex number result would have been 54 minus 4i. When x was 6 and y was 28, we would get exactly that which we're looking for. And then the last one in this set, we have number 20. 15 minus 3yi. 15 minus 3yi, is our fraction? Equals, there it is, 1/2 x plus 2i. Let's go for the x portion first. That's where we have the fraction. We have 15 equals 1/2 x. We multiply both sides by 2, right? Times 2 times 2. Boom, boom. We're going to get x equals 30. And then for I, negative 3y, my y's are getting weird. I think this is the last y I need, equals 2i. We're going to divide both sides by, I guess, I to begin with. And then by negative 3, we get negative 2/3. So we get a fraction y answer. Oh, well. That's the thing that would give you a 2i, though. So that complex number is 15 plus 2i, FYI. Just so you know. Okay. So there is 13 through 20. Now let's start to deal with complex numbers in the very conventional way. I am going to be very quick with these because these should feel no different from what we would do if they had x's, variables. I'm going to combine like terms when I add or subtract. The difference is In standard form, the I comes after. The I comes last, not like an X here. The I comes after because the real part just comes first. We go real first. Okay, so we have 6 minus I plus 7 plus 3I. Now I'm going to show the work the same way I would for if these were X's. I'm going to rewrite this without parentheses, which means there's no change in sign, and I'm just going to combine like terms. Real with real. 6 plus 7 is 13. Negative I plus 3I is positive 2I. Boom. And there's your standard form answer of that. So again, treat it like X. The difference right now being the I term goes last instead of first. And that's it. 9 plus 5I, number 22. 9 plus 5I plus 11 plus 2I. Again, rewrite it without parentheses. Make that make more sense. 9 plus 5I plus 11 plus 2I. We got 9 plus 11, which is 20. And 5I plus 2I, which is 7I. I know the book does a little bit more in the lecture portion on like put it in a factored form thing and put it in parentheses with multiplied by I, which is what we could do with X's, but we never do, so I'm not doing it here either. We have a few of these, and I think they're just going to be, I mean, again, if you're okay with, combining like terms in any other general sense, this is just the same. Now, these are subtraction, and just like we would do before, I am going to rewrite this without parentheses, but by distributing the negative. So this 12 plus 4i remains without parentheses or otherwise. Now I distribute this negative, and I'll have negative 3 minus negative 7i is plus 7i. And then we just combine. 12 minus 3 is 9, and 4i plus 7i is 11i. There you go. Change pages here. 24. We have 2 minus 15i. This is very drill and kill, which is good. The longest part for me is copying down the problem, especially when I have to rewrite it without parentheses, which is, to me, kind of almost a necessary step. You don't want to make a mistake there. So let's rewrite without parentheses. 2 minus 15i minus 4 minus 5i as you distribute the negative. 2 minus 4 is negative 2. Negative 15i minus 5i is negative 20i. Number 25. Back to addition, which I don't know how these problems change compared to the previous addition ones. 12 plus, because generally they progress more. They say, okay, here's what we're going to do differently on these problems, and I don't see what the difference is here. So this will be 12 plus 3i plus 7 plus 3i. 12 plus 7 is 19. 3i plus 3i is 6i. I am, of course, waiting for a problem where you end up having to cancel something and make a 0i out of it or whatever. Oh, I'm sorry. That's what this was. I totally missed a part of this problem. Let me redo that. I'm sorry. Redo. That's where this problem's different. I shouldn't go so fast on this. That was a minus. That was a minus. And I walked right into what this was. Negative 3i plus 3i is 0i. That's where you're just left with 19. A real number. It's 19 plus 0i, but get rid of that, just like 19 plus 0x. Get rid of that guy. It's just 19. That makes more sense. I was like, why are we doing the same thing as we were before? That's a minus. My bad. You're good. You probably caught it. You were yelling at the screen. All right, number 26. We got 16 minus 9i minus the quantity 2 minus 9i. Something's probably going to cancel again here. 16 minus 9i, and then distribute the negative. Minus 2 plus 9i. Ah, yes. Negative 9i plus 9i is le 0, and 16 minus 2 is 4. Remember, it's not minus negative 2. That was part of the negative there. So 14. Excuse me, 14. Okay. 27. Now let's split up some parts. So if we were to speak in real terms, not like real number, real terms, but if we were to speak out loud about what we're doing here, because, people kind of ask, like, why do we have parentheses in some of these things? Obviously, with negatives, it matters by distributing the negative. But why does this have parentheses if it's going to be the same? Because we're saying, here's how we take this complex number minus this complex number. So for this problem, here's what we're doing. We're taking a real number, and then we're subtracting this complex number, this imaginary number, this complex number, and then we're adding this pure imaginary number. They're saying, what's this minus this plus this? As if they're treating them as three separate numbers and we get to combine them. That's all. Anyway, for you, no change in what we do. Distribute this negative to get 7 minus 3 minus 4i, and then plus 6i there. And these are in perfect order. 7 minus 3 is 4. Negative 4i plus 6i is 2i. So 4 plus 2i is the complex number result of adding that real number with that complex number with that pure imaginary number. Number 28. We have 16 minus, same thing, 2 minus 3i minus I. Distribute that negative, we get minus 2 and then plus 3i, and then here's a minus I. 16 minus 2 is 14, 3i minus I is 2i, so 14 plus 2i instead of 4 plus 2i. We're swimmingly moving along. Obviously, problems might get longer as we get farther into it. Number 29, negative 10 plus 6 minus 5i. I'd say the quantity, but it's also just the whole complex number. Minus 9i. Adding this means no change in sign, so 10 plus 6 minus 5i, and then minus 9i. Negative 10 plus 6 is negative 4. Negative 5i minus 9i is negative 14i. And number 30. Number 30 we have negative 3 plus 8 plus 2i plus 7i. Again, rewrite it as it is. 8 plus 2i plus 7i, and negative 3 plus 8 is 5. 2i plus 7i is 9i. So very straightforward, guys. You combine like terms, distribute negatives, all that jazz. Just standard form has the I term last for a complex number. Okay, using structure, write each expression as a complex number in standard form. So on number 31, what we're going to take here for this is a part A. Square root of negative 9 plus square root of negative 4 minus square root of 16. What we're going to do is let's translate these by changing them to their new version. This is 3i, and this is 2i. And remember, it's a positive number, 3i plus 2i there. And then this is 4. We're going to subtract 4. Hopefully that simplification stuff we practiced earlier kind of makes sense now. And I'm going to write the negative 4 first as the real number. 3i plus 2i is 5i. There's your standard form of that complex number. B, let's fit on this page here still. We got the square root of negative 16 plus the square root of 8. Hold on. Square root of 8 plus the square root of negative 36. Square root of negative 16 is 4i. Square root of 8, that's root 4 times root 2, or 2 root 2. It's irrational, but it's not imaginary. It's a real number, no I. And square root of negative 36 is 6i, positive 6i. 2 root 2 is a real number, so we're going to write that part first. It's irrational, but it's real. And 4i plus 6i is 10i. And we're left at that, 2 root 2 plus 10i. All right, number 32. Let's keep moving forward. Number 32. The additive inverse of a complex number z is a complex number z sub a, such that z plus z sub a equals 0. Find the additive inverse of each complex number. So on part A, we have z equals 1 plus I. We need to make it so that we can write some z sub a here where we have the additive inverse of these. There's a real part that has an additive inverse. The additive inverse of 1 is negative 1, because 1 plus negative 1 is 0. And then there's an additive inverse of I, which is negative I, 1i, which is negative 1i, that would make that 0 as well. You're basically changing the signs, and unless they're going to trick us on something here, that's all you're trying to go for. I don't even know why I need to make that blue, but I'll make it black again. But that's what we're going for there. It's just that these parts, they just want to re-remind you of what parts add together. 1 minus 1 is 0, I minus I is 0. You're left with 0 as a result when you add those two complex numbers. Part B, z equals 3 minus I. So we're changing the signs. Z sub a. It's really multiply everything by negative 1. Even z sub a. Z sub a is negative z, right? So you're using that part. Distribute a negative, basically. Negative 3 plus I. That's what gets you 0 when you add that portion. And then C. See, these aren't challenge problems. It's reasoning. They're making sure that you can reason with what you're looking at. Negative 2 plus 8i, and this z sub a would then be positive 2 minus 8i. So when you combine that, you get 0 out with its additive inverse. And that's what additive inverses are, the opposite sign. Okay, that was number 32. All right, numbers 33 to 36. Now, you might want to go to the lecture portion of where we do the circuit stuff, we're going to find the impedance, of the series circuit. And I guess I need to, maybe I'll copy paste that table. Let me just find it. Let me copy paste that table just so we know what we're using with it, from resistor, inductor, and capacitor's resistance or reactance to their whatchamacallit, to their impedance. Okay, so hold on, let me go back one more time. Where's the resistance, reactance component labeled? Reactance. Okay, so those, okay. I just want to say the right word. I didn't want to have them confused. Where was I? There we are. All right, so for this next set, we're going to kind of refer to this table, but even more so, we don't want to get too big into that, I got to memorize this table. No, the figures, and I think I'm going to kind of, I'm going to copy paste these diagrams as well. The figures can help represent what you're doing anyway. That's why I said you might want to hear my lecture portion. If you hear what I talk about with the lecture, now I'll recap it very quickly here on the first problem, but after that, these will go as fast as either use of the table or understanding what we're doing with it to find the impedance of these things. A circuit has a loop, and the loop flows in a certain direction. On this side, with the alternating current, I believe they called it, there's nothing really going on there, but then we have this inductor here where we are going upward, which is perpendicular to this left-right bit, right? But upward, think of upward as positive. But also think of up and down as the imaginary axis. Imaginary axis goes up and down, so think about this I. Then this thing goes to the right, and right to us is positive, like think positive x. And think on a real number line, we go positive numbers this way, negative numbers this way. This is a real portion, resistor, its resistance is here, and how we say this impedance goes there. And then we go downward think negative, and perpendicular to real, you think imaginary. Imaginary is perpendicular to real, and then this closes the loop going over there. So when we're coming up with writing what the impedance is, the resistor's resistance is the same as its impedance. This 12 ohms, and that's the omega symbol, the 12 ohms here, and I don't know, really quickly, I want to go back one more time and see how they write the part where they just say impedance equals, what do they say there? They say impedance of circuit. So I'm just going to put a capital I if you don't mind. So the impedance of the circuit, I equals, we're going to take so there's 12 ohms. Boom. That 12 represents 12 here, a real number. We also have, now it starts with this, and that's why I'm going to write this first. It starts with this 9. This inductor's reactance is 9, and it's a positive 9 as it goes upward in the circuit here, but we're going to write that as 9I because of the direction, the upward direction perpendicular to it. And then the last part, the 7 ohms downward, also in terms of I, as it's perpendicular to the real, and its reactance, its impedance is negative because we're going downward there, so that's negative 7I. So that's all we're writing with this, and I think we're going to make sense of that each time that we write it, either by using this, the R, we attach an I to it, or we change signs like that. So the impedance here will be 12 plus, and 9 minus 7 is 2, so 2I ohms. Okay, that's the overall, I'll put it in parentheses, that's the overall impedance of this circuit. That's how we combine them. So let's try that for number 34. I don't know if that's making sense or not. It's just, you might be still confused and, wait, what are we doing? Why are we doing this? It's really a matter of what we're putting where, because these diagrams, the diagrams are not always the same now that I'm looking at these other ones. But follow the symbols. I think that'll be part of the important thing. My problem is I didn't know what the symbols were or what the names were when you say resistance or reactance. But the process still applies. So as long as we go from inductor to resistor to, what was the other one called? To capacitor, boom, we're going to flow in that direction here to complete a loop of the circuit. That's where that goes positive, and et cetera, et cetera. So here we go. The impedance will take 6I, boom, upward to 6I, plus 4 ohms, and then minus 9I ohms as it goes downward in that case for that guy. So the impedance will be 4 minus 3I ohms. Like so. I cannot do this omega very well. I'll do a lot better on the next one. I promise. I'll really try. Number 35, you can see that the alternating current side is on the left, and we got to follow where we hit the impedance and such. This is where I actually... Hold on a second. It's not pasting. Okay, we're still going based off of the symbols here to make this part work, and so this is where maybe my explanation of the stuff doesn't really apply this time anymore. So maybe I want to be sure that I even get the right answer in the end. I guess this time we're talking more about symbols, not so much about perpendicular to something. So actually now I lost myself in my own explanation from the lecture. So there are probably electrical engineers that are saying, you're saying this thing wrong. And I apologize. I had no intent to. So this circuit doesn't quite work that same way as it did before because the capacitor is perpendicular to the inductor. Interesting. But I will follow the symbols. I will just follow the symbols this time. So based on, I mean, we have the resistor here, the inductor here, the capacitor here. But the inductor and the capacitor, I didn't know that it can work this way. The inductor and the capacitor being perpendicular to each other, it doesn't matter. They still have I. They still have I. So I guess maybe I said it incorrectly the first couple times. Apologies. But in this case, I'm just going to add them as they are. This is the resistor. That will be still a positive. That'll be positive 8 ohms. The inductor will be positive 3I ohms, and the capacitor, excuse me, I keep saying capacitor. I'm thinking compactor. The capacitor will be negative 2I ohms. I suppose, I guess it doesn't change how we do that because of how they talked about how they go here. We're talking about the impedance, and that's what we're going to get. So I equals 8 plus a little I right there. The impedance is 8 plus I. Oops, I didn't do my symbol. 8 plus I ohms. There we go. And lastly, number 36. Same stuff going on there. Number 36. It's just based on the diagram though, right? So we have... Oops. Let me do that again. Yeah, you know, that's why I didn't take up engineering. But the fact that I is used in them means it's important. All right, so the impedance we're going to take, here's the resistor with a resistance of 14 ohms. The inductor has a reactance of 7 ohms, so its impedance is 7I. And the capacitor, I just said it again. The capacitor has a reactance of 8 ohms, so that's negative 8I ohms of impedance. So we're going to do I equals 14, and then 7I minus 8I is negative 1I. So that many ohms of impedance overall for that guy. Okay. That was those ones, and I'm kind of glad to get those ones out of the way. Not a lot of word problems with these ones. Those might be the only ones in general. They're obviously going to ask you to do different things on these other problems. But all right, numbers 37 to 44, we are going to multiply. So this is, if you missed the lecture portion, we treat this exactly like we would with x's, with the one big exception that I squared, I'm going to write this right here, that I squared equals negative 1. Because if I equals the square root of negative 1, you square both sides, I squared equals negative 1. You multiply two i's together, two imaginary, pure imaginary numbers together, you get a real number out, where the sign changes too, no less. Anyway, I distribute. 3i times negative 5 is negative 15i. 3i times I is 3i squared. However, because I squared is negative 1, that becomes negative 15i minus 3, right? This becomes 3 times negative 1, so that becomes negative 3. But my final answer, I'm going to write the real part first. So negative 3 minus 15i, like so. That's what happens when you multiply that thing. Number 38, you have 2i pure imaginary times this complex number 7 minus I. Let me do that again. Let's distribute. 2i times 7 is 14i. 2i times negative I is negative 2i squared. Because I squared is negative 1, this actual thing is negative 2. We're subtracting negative 2, which means plus 2. Basically, get rid of the I squared, change that sign. It becomes plus 2, a positive 2. Positive 2 plus 14i is the standard form version of that we are going to write. And that is the answer. Now we're going to multiply binomials times binomials. We have number 39, where we do 3 minus 2i times 4 plus I. This is where we FOIL. So I won't write this part very often, or I won't do the arrows probably in any other sense, but I want to remind you of what we're doing. 3 times 4 is 12. 3 times I is 3i. Negative 2i times 4 is negative 8i. And negative 2i times I is negative 2i squared. So we get a couple things to do here. We get to combine like terms with the 3i minus 8i to get negative 5i. But the negative 2i squared, we just saw this on the previous problem, I believe. It's plus 2. And 12 plus 2 is 14. So we get 14 minus 5i as a result of that. So the I squared comes into existence here with foiling. We don't just multiply real with real. It's every part that does get multiplied when we're doing that. It still applies, just like it would for variables. Number 40. We have 7 plus 5i times 8 minus 6i. And we get to FOIL again. So 7 times 8 is 56. 7 times negative 6i is negative 42i. 5i times 8 is 40i. And 5i times negative 6i is negative 30i squared. So now we get 56. Negative 42i plus 40i is negative 2i. And this becomes plus 30 because the I squared is negative 1. 56 plus 30 is 86. You're left with 86 minus 2i. Okay, number 41. We have 5 minus 2i times negative 2 minus 3i. 5 times negative 2, 5 times negative 3i. Negative 2i times negative 2, positive 4i. And negative 2i times negative 3i is positive 6i squared. You know, just like, I mean, students often forget to do the I squared, x squared, things like that. You cannot forget the I squared here. Same way. This will become a real number. So this becomes negative 10. Negative 59 plus 4i is negative 11i. And 6i squared is also negative 6. Negative 10 minus 6 is negative 16. We have negative 16 minus 11i. Number 42. Number 42. So number 42, we have negative 1 plus 8i times 9 plus 3i. Negative 1 times 9, negative 1 times 3i, 8i times 9, and let's see if we can do this one in one step. 8i times 3i being 24i squared is negative 24. Boom, in one step. You're going to ask, well, how'd you do that? You had to listen to me. 24i squared. Negative 9 minus 24 is negative 33, and negative 3i plus 72i is 69i. There we go. Number 43 and 44, we have a squared thing going on of a binomial. Doesn't change how we work out the binomial squared. I'm going to do the shorthand version of this. The first time I'm going to write out how we work it. We do a squared minus 2ab plus b squared, which becomes 9 minus, we double 18i, which is 36i, and then we have plus 36i squared, or minus 36. Plus 36i squared is minus 36, and 9 minus 36 is negative 27. So we have negative 27 minus 36i. No, we don't just square this and square this, right? We don't just square those two things. Number 44. I'm going to do this one in one less step. 8 plus 3i, quantity squared. Square the first term. Double the product of these two. Double 24i. Oops. I said what I wanted to write and I wrote what I wanted to say. Double 24i plus 3i squared. That's 9i squared, which is negative 9. Boom. 64 minus 9 is 55. 55 plus 48i. Okay. In exercises 45 and 46, justify each step in performing the operation. Okay. Well, they write things differently than I would, so I'm just going to go ahead and copy and paste what this thing is because I want to write the answers straight in there. So sorry if you got to write more in copying this stuff down. If I write less, that's more fun for me. I just got to shrink what I got there. Okay. Well, I mean, I don't even know how to say what I want to say for these. Justify each step. 11 minus 4 minus 3i plus 5. I don't even know how to answer this. We are, maybe I should read an example on how you do this. You combine, let's see. I know this one is 11 minus 4 became 7, so combine real numbers. Real numbers. Now, what I'm seeing here is they are interacting this real number with this complex number to begin with. So associate real numbers. By that, I mean I am letting the 11 and the 4, the negative 4, associate with each other so they can ultimately subtract. But we're only doing it with those two. We're not even interacting the 5i yet until we've kind of distributed that negative. Distribute negative as well. Maybe that's more so what they wanted to say with that. And now we're going to associate the imaginary numbers here. Notice how negative 3 and 5 are going to work together because they both have i's with them. So associate imaginary numbers. I don't know if this is the best phrases to use. And then we combine imaginary numbers. I don't know. Kind of weird question. Not weird, but since I don't write it that way, and since we don't generally describe things like that, I just say combine like terms. But the way that they have things written when it comes to that stuff is going to be a little bit different. 46 looks like a different kind of question in and of itself anyway, because this time it's foiling. So I'm probably going to say something along that concept. So number 46, I'm just glad I didn't have to write all that. Number 46, let's justify each step. And the step has to do with going from one part to the next. So what they're saying is, what did you have to do to go from here to here? So from here to here, we foiled. Foil. I'm going to trust all of it's correct. This is not an error analysis question. Let's hope the book doesn't have a typo. Then they combined imaginaries. Combine imaginary / they also turn I squared into negative 1. We made it real. Right? Simplified. Simplify. Negative 8 times negative 1. And then also more simplify. We combine like terms. Combine real. 21 plus 8. Whew, kind of glad I'm off those problems. I don't know if those descriptions are best. Obviously, an answer key might say something much better because it's what they expected, but it'll work for me. All right, in exercises 47 and 48, place the tiles in the expression to make a true statement. Okay, interesting. So it's kind of like a shuffle things around until they work. So we got to figure out how to make something minus something I minus, oh, this is interesting, minus something I to equal 2 minus 4i. So the interesting part about, I mean, it's literally using their numbers, so it's guess and check kind of until it works. But I wonder if there's a way that I should write this simplified, as in, because this is a minus, right? It's actually something minus something I minus, excuse me, minus something. I think I'm allergic to something in my own room. I haven't sneezed in like 2 weeks. And it's something plus something I right here equals 2 minus 4i, because we're distributing this negative, right? This thing distributes like that. Let me take care of sniffles for a second. Okay, so we're back. So anyway, I'm kind of distributing that negative because what I really want to do is come up with the whole, and it's weird to write blanks. I almost want to write variables like x, y, w, x, y, z or something like that. But anyway, we need something to make 2 by doing this number minus this number, right? So something minus something equals 2, basically. This minus this equals 2 is what we have to come up with. And then this I, this negative this I plus this I needs to equal negative 4I, which means negative something plus something needs to equal negative 4 among these numbers. So that's kind of my cleanup version. I'm sure you guessed and checked and got this answer much faster than I did by doing that. But what minus what can give me 2? 6 minus 4 can give me 2. And is that the only one? 7 minus 4, no. 7 minus 3, no. 6, just 6 minus 4, right? So I imagine this will probably be 6 minus 4 that gets me 2. So we're going to fill in this front part in the end. And then that's left. Sorry, what do we need next? Negative 4i. So negative 3i plus 7i gets me negative 4i, right? So your final answer, how we want to write that 6 goes here. That 4 goes there. So this is basically the 6 minus 3i. So we have 6 minus 3i minus, and then here we got 4 minus 7i. 4 minus 7i, which would equal 2 minus 4i. Let's see if we can kind of mentally confirm that that is correct without distributing a negative. But 6 minus 4 is 2, and negative 3i minus negative 7i. Oh, that didn't work. Oh, it needs to be negative. Oh, I messed up. I thought it needed to be positive 4. This, good thing I confirmed it. Negative 7i plus 3i. So, let's do that one more time. Make those green. Not that light, like that. So that's I have that wrong. Negative 7i and negative 3i. So, boom and boom. Okay. 6 minus 4 is 2. Negative 7i minus negative 3i is negative 4i. Yeah, that seems to work out. Okay. Maybe I don't have to divulge as much. Oh, well, this one's different because it's multiplication. So number 48, and I know there are the blanks and such, but I think cleaning it up really gets your check to be a lot better. So we'll see if that works here. Again, you can come up with these answers so much faster with these things, but I really want to hit home what we're doing with it just in case it's not as easy as you think. Okay. Equals negative 18 minus 10i. So let's really work on this left side here. This would obviously be a distribution of these sets of numbers. So you have something times something I, right? Something times something I plus, now we're going to have something I times something I. So something times something I squared, right? Through that distribution. Now, when you turn something into I squared, it'll turn negative. That means this will turn negative. So I'm going to rewrite this guy in front right here, where we got to find out a negative something times something here. And that needs to equal, by the way, negative 18. So this thing, let's just keep that blue, or blue. So this something times something needs to equal negative 18. That means the something times something needs to equal 18, right? But just I need two numbers to equal 18. And then this other part, something times something I, needs to equal negative 10i. So let's use blue over here. So something times something I needs to equal negative 10i. And, you know, I could simplify things more, meaning just make something times something, something times something be 18 and something times something be negative 10. But let's see if we can work that out here. So there are three numbers in the end. So that one thing needs to be the same in both, right? We need to lock the same number in place because it distributes. So it's the same something here that goes into both of these. And that probably would have been a lot faster for us to not do it this way. But 2 is a common multiple of both of these numbers. So I think it's important that this is the 2. That must mean that this would have to be the negative 5. And this being a positive 9 is still fine because negative 2 times 9 is negative 18. 2 times negative 5 is negative 10i. So I think that'll work there. So ultimately, when we write this, this is the 2. Yeah, I did this really slowly this way. I'm sorry. I was trying to make magic happen out of this. This is negative 5, and this is 9. Yeah, that went very slowly for me, discovering this. So it becomes 2i times negative 5 plus 9i equals negative 18 minus 10i. I'm sure there's a time and place where what I wrote is going to be a lot faster with what we did. And listen, maybe it would go beyond you to realize that, the negative 18 comes from multiplying two positive numbers together and such. So I think it's still good to look at with that I squared portion. It's not like that was hopefully completely lost on you. Okay, let's keep moving forward from those daring problems. In exercises 49 to 54, this is what you get when you have someone who didn't look at the problems beforehand. That's part of the exotic nature of this that I enjoyed doing with you guys. I'm seeing it for the first time, as you probably are. So it doesn't look like I have tricks up my sleeve. Except for what I know. In 49 to 54, multiply the complex number by its complex conjugate. So we have 1 minus I. Now its conjugate is 1 plus I. Okay, so we're going to multiply 1 minus I times 1 plus I. Now the first time, I'll go ahead and do the FOIL stuff. After that, I'm going to talk about it as a difference of two squares. So this becomes 1 times 1 plus 1 times I minus I times 1 minus I times I. These cancel, and they always will for conjugates. That's the point. We make a real number out of this. Negative I squared is positive 1. 1 plus 1, which is 2. Okay. Now, what did we do? We did an A plus BI times A minus BI. This will equal, where you FOIL everything out, this will equal A squared plus B squared. Straight up. A squared plus B squared. No I. No I. And whatever we square turns positive. We're going to be adding two things. Let's try it with the next one. Number 50. Number 50. We have 8 plus I. Its conjugate is 8 minus I. So we're going to do 8 plus I times 8 minus I. Now, this equals the sum of two squares. We're going to do 8 squared plus, not I squared. B is the number multiplying by I. In this case, that is a 1. A 1. 8 squared plus 1 squared. So that's 64 plus 1, which is 65. You can FOIL it. You're going to get the same answer. So, there we go. Number 51. I guess we don't, I don't think it happened in the other parts as well, but I guess we don't rationalize denominators with these things. That would be the goal. We would use this to rationalize denominators. They don't have you do it here. Maybe it's in the next section. 4 plus 2i. Its conjugate is 4 minus 2i. So 4 plus 2i times 4 minus 2i would give you 4 squared, 16, plus 2 squared, 4, 20. Yes, I'm working faster over time with these. And how they work, a squared plus b squared. It's faster when you know what you're doing. I keep, because, trust me, I'm going to have students that'll ask me, wait, where'd these numbers come from? How'd you do it? This is the sum of two squares. That's what it is. That's what happens as a result. I'm filtering out the steps that will get me here later. This conjugate is 5 plus 6i, so 5 minus 6i times 5 plus 6i, which will get me 5 squared plus 6 squared, which is 61. Number 53, negative 2i plus 2i. Now, or negative 2 plus 2i, excuse me. Yeah, it's conjugate. We're going to do the minus bi thing. So we have negative 2 plus 2i times negative 2 minus 2i. The negatives ultimately don't matter here. I'm squaring negative 2. That still gets me 4. And then I'm squaring a positive 2 here, which gets me 4. 4 plus 4 gives me 8. And then number 54, negative 1 minus 9i. Again, it doesn't matter how many things are negatives. The fact that we turn one of them positive in the complex conjugate fashion means we're going to get the right things to cancel. So we're going to multiply negative 1 minus 9i with negative 1 plus 9i, like that. And then you're left with negative 1 squared, which is 1, and then plus 9 squared plus 81, which is 82. Okay. Number 55, an open-ended question. Write a pair of imaginary numbers whose product is 80. The only way to get imaginary numbers, get a product as a real number, is you need complex conjugates to make that happen. In other words, we need some a plus bi times a minus bi to equal 80, or a squared plus b squared. A squared plus b squared to equal 80. So we need two numbers that will work this out, that when we square them, we get this. It's open-ended. There's more than one answer. Now, we could go with the irrational route. I'm trying to think, because I don't know, are there any two perfect squares that get me 80 straight up? 1 plus 79, no. 4 plus 76. I'm going upwards. 9 plus 71, 16 plus 64. 16 plus 64 works. So if I had, in this case, 16 being a squared is 16. So a, listen, it's plus or minus 4. You can use either number. That doesn't matter. B squared this is why it's really open-ended. B squared is 64 and B is plus or minus 8. Man, there are so many ways I can write this answer here. So write a pair of imaginary numbers. We could do 4. We could do 4 plus 8i times 4 minus 8i. Boom. This could be an answer like that. That would get me 80. We could do, this is just so many options. We could do negative 4 plus 8i, negative 4 minus 8i, like that, We could swap these. We could do 8 plus 4i, 8 plus 4i, 8 minus 4i, right? So these are kind of different versions of these answers we can do with real numbers, and then negative 8 plus 4i, negative 8 minus 4i. These are good ones with, rational numbers. With rational numbers that do work. Is there another set? I'm not going to write more of these outside of ones that could be irrational, like 1 plus root 70 plus I root 79 and 1 minus I root 79. Those will work because root 79 squared is 79. It's at 64 and 16, right? So 55, no, 55, 36, 44, no. So those are the only ones that work for rational numbers, I suppose, that'll get you there. And that's a bunch of combinations for that. And I like it. It works out. All right. Gets you back in that sum of two squares concept. So you're doing less guess and check outside of your perfect square bits. Write the complex conjugate of 1 minus square root of negative 12, then find the product of the complex conjugates. So, kind of baiting you here. They have 1 minus root negative 12. I might have said negative root 12, sorry. The conjugate would, I guess, technically be 1 plus root negative 12. Now, I wonder if they don't want us to turn it into I this time. We can kind of do both, right? They say find the product. Let's do it when it's still a square root of a negative, because if I do 1 minus root negative 12 times 1 plus root negative 12, that will still equal 1 squared, boom, plus root negative 12 squared, which is like that. So we're adding the negative. This will become negative 11. Now let's see if that still works if I do, say, if I call it I root 12, or even 2i root 3. So if instead, as an alternate thing, we can turn this into 1 minus, let's see, what would I call it? 2i root 3 times 1 plus 2i root 3. It's going to be the same answer. I'm just saying, I wonder how the appearance changes things. Well, it actually shouldn't really change much of anything when you end up squaring them, okay? Here, I'm going to first write the part when you square it. 1 squared plus, I'm not going to do the plus yet. We'll do it as a difference of two squares to start. We'll do minus, it's a squared minus b squared, so bi squared, b squared, I can't say that right. 4i squared times 3, because root 3 times root 3 is 3. So now we'll get 1 minus, and this is negative. Negative 4 times 3 is 12. Minus negative 12. Oh, hold on. Did that change? Oh, you know what? I made a mistake here calling this a plus. Give me 1 second. See, it's a good thing I double check these. This is not a plus because this is still a difference of 2 squares. There's no plus that appears because there was no imaginary that appeared. That's my mistake. I apologize. That's my mistake. This is still a difference of 2 squares as long as there's no I. I didn't put I in here. So this does become 13. So we will still get that same thing. So it's a good thing that I did put that in, that we checked this thing. So the answer should be the same, and that's where it is. Difference of 2 squares, like that. Okay. Number 57. Expand 57. Expand a minus bi quantity squared and write the result in standard form. Use your result to check your answer in exercise 43. I might have used that format for it before, but because we are now looking at it with just these letters, we'll see. All right, to expand this thing, we're going to say we square the first term. We subtract double the product of these two. And then we square the third term, b squared I squared, which becomes a squared minus 2abi minus b squared, like that. So let's use the result to check our answer. Well, I mean, I did this in those problems. So, I mean, there's the result. But number 43, let's go back a few pages. Excuse me. Number 43, I had 3 minus 6i squared. So let's try this. 3, I mean, this is literally what I did before. So minus 6i squared, so 6. Like that, right? I think that's how I'd write it. So, 3 squared, excuse me. So 9 minus double it, 36i minus 36. Negative 27 minus 36, 36i. Is that what we got the first time? Negative 27 minus 36i. Yes, it is. So that we get the same answer for that one. Okay. Let me pause for a second. Okay. Sorry, I'm back. All right. Anyways, that one checked out right there. We're all good. All right. Number 58. I think it's the same question. They're just having us expand the other one. So it should look very similar. So number 58, we are going to expand a plus bi quantity squared. So we square the first term. We double the product of the a and bi, and then we square the last term, this b squared I squared. So it's going to be the same look, only this time it's a plus in the middle. Plus 2abi minus b squared. And there's the result. Now, number 44 had the thing here of, whoops, went too far back. Number 44 had 8 plus 3i quantity squared, and we got 55 plus 48i. So 8 and 3. 8 and 3. So let's check that. 8 squared plus 2, 8, 3i minus 3 squared. I mean, the problem is I'm doing the same work, right? So it should be the same, it should be the same answer. So 64 plus 8 times 3 is 24, doubled is 48. Minus 9, 64 minus 9 is 55. So again, I'm doing the same. I don't know if they expected you to FOIL in some cases versus others. If this expansion meant don't do that, but we're doing the same work. So same answer as it should be. Okay, error analysis. This came a lot deeper than normal. Maybe they really had to have you practice different kinds of problems before getting here, but let's take a look. In exercises 59 and 60, describe and correct the error and writing the answer in standard form. So in this first one, because I see an error, but let's check the math. 3 times 5 is good, and good, and good, and good. They combine like terms properly. Now, here's where their mistake kind of comes into play, and then we'll correct it. We'll go off of what they had at the end to kind of write it. Actually, not the end, but the step before. Standard form of a complex number should appear in the form a plus bi. So only 2 numbers and the thing second. Also, I squared, it's really the first thing, but I squared is negative, I squared is negative 1. So we got to work that part out. So on the step where they do have 15 plus 7i minus 2i squared, we should be turning that into 15 plus 7i plus 2. And then we do 15 plus 2 to get 17. So 17 plus 7i, the real number, goes first, the real part, and the imaginary part goes second on 7i. There's that fix on 59. Number 60, I see the mistake in the very beginning, so we're going to have to kind of redo the whole thing. This is where I yell on my papers to my students whenever I write comments. So we're going to go straight from the beginning. 4 plus 6i squared, guys, is not 4 squared plus 6i squared. You do not distribute the square. This goes back to the old ages of section 2.3, where I say a plus b squared does not equal a squared plus b squared. And I kind of leave all these kinds of things. I do that to my students all the time. Anytime they do that, I've reminded them. I've let them know we've used real number examples to make sense of this stuff. And yet they still do it. I don't know why. They still do it. They still do it. They still do it. I'm going to give them this problem for homework. Okay. So I should give them both problems. So for this number 60, how do we fix it? Well, let's go from the beginning. 4 plus 6i squared. You know what a squared, a plus b quantity squared is? It's a squared plus 2ab plus b squared. We square the first term. We double the product of these two terms. And then we square the last term. So that's what we do. There is an a squared, there is a b squared, but we do more. Anyway, listen, the rest of their work is correct. They squared the 36i, I squared to get negative 36, and they subtracted. All that's fine, but there's a middle term that they're missing. So we get 16. This is negative 36. That all works out, but there's this middle term. Double 24, which is 48. So 48i, and 16 minus 36 is indeed the negative 20, but they're totally missing this imaginary number portion of it. This imaginary portion is negative 20 plus 48i. Okay. Number 61. Oh, I thought this was a bunch of different problems. It's just one problem? What? Oh, no. Oh, that's rude. I thought this was going to be a bunch of different problems we were going to be able to do. Well, fine. Then I'm going to show less work. Oh, I don't know. I can't. Wow. Okay. Okay, so let's see what they want me to do. Classify your results in the table below. So, okay, I got it. Every result goes in one part of this table. So we're going to write them all. Then I'll plop them in the I'm going to write them in the table on this side, if that's okay, because then it stays on this page. I hope that works. So that's a lot of questions. Eight questions. All right. Negative 4 plus 7i plus negative 4 minus 7i. That becomes negative 4 plus 7i minus 4 minus 7i. 7i's are gone. Negative 4 minus 4 is negative 8. So negative 8 is a real number. Negative 8 will go. I have to kind of use my mouse on this side. But negative 8 will go here. I don't know how many I got to fit. So I imagine not too many. There are only 8 questions. So at most, they're probably going to give me 3 per. At least 2. So there's A. B. We got 2 minus 6i minus negative 10 plus 4i. What is 4i's that can't see? So this is 2 minus 6i plus, so we're distributing the negative, plus 10 minus 4i. 2 plus 10 is 12. Negative 6i minus 4i is negative 10i. There we have that. This is an imaginary number. Not pure, but just imaginary. Okay, here's what I'm going to do. I'm going to copy and paste that. Oh. Let's do that again. What was it? 12 minus 10i. I'm going to write it small enough and clean enough. 12 minus 10i. Okay, let's get that first. Copy, paste. Oh, whoops. Copy, paste, and stick it in there. There we go. Because it's weird how my computer thing's set up, but basically I can't really write on that side unless I drag the whole window over. So I don't want to use the mouse to handwrite all that. Part C. 25 plus 15i minus 25 minus 6i. It's only natural that they have a pure imaginary number here, I think, next. 25 plus 15i minus 25 plus 6i. So we distribute the negative. 25 minus 25 is 0. We're going to have a pure imaginary number, 15i plus 6i, as 21i. So 21i is pure imaginary. There we go. All right, part D. My letter thing is spacing out more and more. I got to kind of bring it back. Reel it back in, folks. There we go. A little better. Part D. 5, okay, this is foiling. 5 plus I times 8 minus I. 5 times 8, 5 times negative I times 8, I times negative I. Negative I squared is positive 1. So we're going to be left with 41 plus 3i. Excuse me. There must be dust in my room. I need to get my purifier back. 41 plus 3i. Okay. Imaginary number. Oh, that did not copy. Come on. No. All right, why aren't you copying? There it goes. I might have to fit one more. I have no idea. It's likely there might even be more than that. We'll see. This is only part D. Okay, E. Back to not foiling. 17 minus 3i plus negative 17 minus 6i. We got that 17 minus 17 is about to happen here. Negative 3i, I should write this first. So 17 minus 17 is 0. Negative 3i minus 6i is negative 9i. Pure imaginary. I want a real number back, homie. F. This is all for one problem. Come on now. Negative 1. I believe the last video I did, because I haven't done one in like 10 days. I believe the last video I did was that like quadratic formula thing. And when I did, there was that one problem. It was getting near the end of the problem set. And wow, it was long. It was a long problem. I even had to pause and write things out just to fit enough video room, just fit enough room to record the video. Oh, it was way too long. All right, I'm going to go faster on this part here. We're going to have negative 11. Actually, no, there's no need to go faster. I still have to combine things at the end anyway. There's plus I and then plus 22i. 2i times negative I is negative 2i squared or positive 2, so plus 2. Negative 11 plus 2 is negative 9, and I plus 22i is 23i. I hope this was the last imaginary number one because I want to kind of fit them all in here and have to shrink things later. So let's see if that, that doesn't even fit on in its own right here. I guess I could shrink them this way. Okay. Part G. Parte G. We have 7 plus 5i plus 7 minus 5i. I think you see where this is going. These guys are gone, and 7 plus 7 is 14. Whoops, let's 14. There we go. And the last one, there was only one where we did foiling. I was hoping, no, actually there were two. Last one, part H. Notice how there's no part I. They'd be like, I don't want to confuse you. Negative 3 plus 6i minus negative 3 minus 8i. Get rid of this other little guy right there. There we go. Minus 8i. Okay, so this is negative 3 plus 6i. Let's distribute the negative. Plus 3 plus 8i. Negative 3 plus 3 is 0. 6i plus 8i is 14i. That is a pure imaginary number. Let's bring that in. And like I said, at most 3 and at least 2. They were kind enough to do that for us. They really should have put a complex conjugate thing in there. I think that would have made more sense to get one from a real number standpoint. There's the table for that set that we did. I hope that makes sense how I filled that out. Okay, and I'll kind of leave that on the screen as we go to the next set, because it's the bottom of the page anyway. Hold on. Sorry, I'm taking care of syphilis right now. Hope we're good. Okay, number 62. Making an argument. The product property of square roots states the square root of a times square root of b is root ab. I agree. Your friend concludes square root of negative 4 times square. This is a good question. Square root of negative 4 times square root of negative 9 equals square root of 36 equals 6. Is your friend correct? Explain. Well, this is actually a good question. Because does it quite work in that way? You know, we already saw, before I write it, we already saw when we did something like the square root of, I think, negative 12 squared. It's just negative 12, right? The thing inside kind of doesn't, we don't square that 12, the negative 12. We squared the square root. So there are other parts that take precedence before. Just keep that in mind. So does square root of negative 4 times square root of negative 9 equal 6? That's the question we're asking ourselves. Now, the way that they showed it totally makes sense. But there's something happening before it that we got to be careful of. And that's the I thing. Square root of negative 4 is 2i. Square root of negative 9 is 3i. So does this equal 6? Well, 2 times 3 is 6, but I times I is I squared. You get 6i squared. Does 6i squared equal 6? 6i squared is negative 6. Negative 6 does not equal 6. No. I mean, this is my explanation. You have to take care of the square root portion first before interfering with it. We never had that problem before with numbers being positive. But now that numbers are negative, there's an order of operations that happens. The square root takes place before. Square root's not part of PEMDAS, but it's part of the parentheses. It's a grouping. The square root takes place before multiplication. That's kind of why. And so we took care of that first. We did that part first, and that's how it went. Okay, let's do number 63. Actually, here, give me one more second. I have to take care of one thing. Okay, I'm back, and I just saw the score. Lakers losing to the Kings. All right, 63. Make a table that shows the powers. Ooh, I like this. From I to the first power to I to the 8th power in the first row, and the simplified forms of these powers in the second row. Describe the pattern you observe in the table. Verify the pattern continues by evaluating the next 4 powers of I. Well, all right. I like the problem, but I was like, I don't know if I want to do the next part. All right, so I'm going to have this kind of table here where, forgive the ugly looking column portion, but we're going to go like this. I might have done 8 right there. So we're going to go from I to the first power to I to the 8th power. Now, keep in mind, y'all, I is the square root of negative 1, and therefore I squared is negative 1. Remember, we take care of the square root part first, and the inside thing does it. Now, I cubed, okay, I'm going to kind of like say this out loud, but I cubed is I squared times I. So if we're actually, I'll write this. If we're multiplying this by I, then negative 1 multiplies by I. And that makes I cubed equal to negative 1 times I, which is negative I. Now, the next part depends on how you want to multiply these things. You can either multiply I cubed times I to get I to the 4th. This is how I'm going to write it out first, and I'll say the other one out loud, I to the 4th. And multiplying negative I times I gives you, and actually I'm trying to decide if I want to write this one or if I just write I. So I'm probably going to write I right here. It just gets a little weird. But negative I times I is negative I squared. I squared is negative 1. The opposite of negative 1 is 1. I to the 4th power is 1. Now, when we go to I to the 5th, we multiply this thing by I again, and then we get I out. That's why I'm saying I might just want to put an I here. So I'll put I here, and I'll just put I to the 1st on top. So I to the 1st is I, etc. But I was explaining why the negative 1 came to be. So I to the 5th, and there seems to be a repeat of what we do. I times I is I squared, and we get negative 1 here. So I to the 6th is negative 1. I to the 7th is negative I, and I to the 8th is 1 again. I repeated the pattern without kind of saying that it was. But yes, there's a pattern repeat. You can see where it shows up from these. The thing I was going to say that I could have done for I to the 4th, I could have done I squared times I squared. I squared times I squared is negative 1 times negative 1, which is also positive 1. We would get that same thing from it. I don't want my ones to look different, so I'll put them like that. Okay, so there is that pattern. They said now expand this into the next 4 that we would do. So I to the 9th, I to the 10th, I to the 11th, I to the 12th. I'll just write it here. I to the 9th is then therefore I, the equivalent of I. I to the 10th is negative 1. I to the 11th is negative I. And I to the 12th is 1. So what's I to the 167th? If every multiple of 4 gets us back to I again, gets back to 1, because I to the 4th is 1, then do multiples of 4 up to like 167, right? 160 is a multiple of 4. So I to the 160th is 1. So I to the 164th is 1, and I to the 168th is also 1. So I to the 167th is going to be the same as I cubed. It's going to be negative I, right? So that's how that works. And I don't know if they're going to ask us to do one like that, but that's what it does. It keeps repeating itself over and over again. So I don't know if I was supposed to identify this, but just by maybe boxing this thing here, where I'm going to say this thing repeats. And hopefully that kind of answered everything with this. There's use for this, obviously. It's not just about I and I squared. We should always have a real number. I should never be raised to a power in the n through simplification. The number will either be imaginary or real. It'll either turn it negative or positive, maintain what it was, anything like that. But it should not have any exponents to it. You simplify that portion, and that's exactly what we just did. I can see number 67. Okay, I can see them do that here. So we're going to use those down below. We're not at that problem yet, but just that's where 63 is going to lead us. Okay, number 64. Number 64. The coordinate system shown below is called the complex plane. This is where they're bringing it up. And where I was trying to do it with the circuit stuff, I don't know if it actually applied fully, but here's your real axis. Think of your real number line. You know, a number line where you have, 1, 2, 3, 4, 5, negative 1, etc. Don't think of it as x and y, although you kind of can. In the complex plane, the point that corresponds to the complex number, yeah, it's like an x and y. A plus bi is a comma b. So think of it like x and y. Left, right, up, down. What are the numbers that work there? Match each complex number with its corresponding point. Okay, so work-wise, all I'm going to do is this. I'm going to say A. So 2 is also, by the way, 2 plus 0i, which means the ordered pair that it corresponds with is 2 comma 0. If it's 2 comma 0, that point is D. You can see where D is at 2 comma 0. So that's how I'm going to do the work. B, 2i is also 0 plus 2i, which means this ordered pair component is 0 comma 2, which is on F. Which F is on, which is F. C, 4 minus 2i has the corresponding ordered pair 4 comma negative 2, which looks like that's B. I'm going to go pretty fast here. D, 3 plus 3i corresponds to 3 comma 3. 3 comma 3 is point E. Part E, negative 2 plus 4i corresponds to negative 2 comma 4, which is point A. And then part F, negative 3 minus 3i corresponds to negative 3 comma negative 3, which is C. All right. Cool. Yeah, those totally apply. If you take was it pre-calc when we start taking the magnitude of those or something? It might be pre-calc when you start doing that. All right. Numbers 65 to 70, write the expression as a complex number in standard form. So I just brought this up with number 63. This table's application will apply. This last question they did is pretty notable for what we're going to do, but we can probably use the table. These numbers are probably small enough to use the table, I'll be honest. But we'll see what we get here. Now, there's still a form of a combining like terms bit that we can try and do wherever. This first question actually is irrelevant to it. But let's take a look. Just bigger sets. 3 plus 4i minus 7 minus 5i plus 2i. It's just asking you to do some work. 9 plus 12i. We did a lot of drill and kill in the beginning, guys. I'm going to go pretty fast here. Not even I don't know. I'm just going to go pretty fast. I've explained it now. Now I'm kind of doing the problems until there's something new I got to teach. So this is 18i plus 24i squared is minus 24. Now let's combine. 3 minus 7 is negative 4. Negative 4 minus 24 is negative 28. 4i plus 5i is 9i, plus 18i is 27i. So unless I messed up a number somewhere while talking, hopefully I distributed everything correctly, and that's what we would get for 65. 66, it's like a variation of 65. That's what they tend to do, odd with an even. Work it out that way. 66, 3i times 2i, or 2 plus 5i, plus 6 minus 7i minus 9 plus I. Okay. Distributing, we get 6i plus 15i squared, so minus 15, plus 6 minus 7i minus 9 minus I. Distribute. Negative 15 plus 6 is negative 9. Negative 9 minus 9 is negative 18. 6i minus 7i is negative 1i. Negative 1i minus I is negative 2i. So there you go. I was expecting stuff to cancel almost, and they just didn't want to. 67. We have 3 plus 5i times, okay, here's one of these. 2 minus 7i to the 4th. Okay, you have two ways of going about this. You can either leave it as it is, or you can change it now. I want to change it now and simplify. Remember what I to the 4th is? It's 1. Where is it? I to the 4th is 1. So you know what negative 7i to the 4th is? It's also negative 7. So we can do, oh my goodness, we can also do 3 plus 5i times 2 minus 7. Or 2 minus 7 is negative 5. We could do negative 5 times 3 plus 5i. We can take care of it early on. That's probably what I'm going to do. Take care of it early on and simplify it so then we get to this stage. Negative 5 times 3 is negative 15. Negative 5 times 5i is negative 25i. You could also FOIL it, right? You could also FOIL it, but then you have to simplify more things with it. So simplify earlier first will prevail, I believe. I'm going to just work off of that. Hopefully you're okay with that. Same thing on 68. So number 68, we have 2i cubed times 5 minus 12i. I cubed is the same as negative I, so this becomes negative 2i when you work that out. So 5 minus 12i. Negative 2i times 5 is negative 10i. And negative 2i times negative 12i is a positive 24i squared, so negative 24. So we get negative 24 minus 10i in standard form. Number 69, we get to simplify things again here. They get more crowded. We have 2 plus 4i to the 5th plus 1 minus 9i to the 6th minus 3 plus I to the 7th. Okay. Kind of doing two steps at once. I'm going to write above what I can translate this to. I to the 5th is the same as I, so this is the same as 4i here. I to the 6th is the same as I squared, which is the same as negative 1. So this guy will become a negative 9. We'll subtract negative 9, right? I wonder if I should just put plus 9 then. Oh boy, that's going to be a little weird. What should I write? I'll just write the negative 9, that's fine. And then I to the 7th is the same as I cubed, which is negative I, just kind of, it's the remainder if I divide it by 4. So there's a negative I with that. So this will be rewritten as, without parentheses, 2 plus 4i plus 1. Now we're subtracting negative 9, right? Subtracting negative 9. So that'll be plus 9. And then this negative I, so it's negative 3, hold on, minus 3. And then we're going to subtract negative I, so plus I. I don't know, maybe it would have made more sense if I just wrote the other step. So 2 plus 1 is 3. 3 plus 9 is 12. 12 minus 3 is 9. So we get 9. And then 4i plus I is 5i. 9 plus 5i. Okay, number 70. We're almost done. We got... wait, was there a number 74? Oh, yeah. Wait. There is no 74. I said to 74. Maybe there's a 74 and I just missed it. It's to 73. Oh my. Oh, there is a 74. Yeah, there is. Forget what I just said. I don't know. Sorry. Forgive what I'm doing right now. What did I say? Number 70. Sorry. My bad. Okay, 8 minus 2i to the 4th. So 5 more problems. Plus 3 minus 7i to the 8th. Minus 4 plus I to the 9th. Okay, you know what? I think I'm just going to rewrite the steps as they are. So, even with parentheses. So 8 minus, so I to the 4th is 1. So 8 minus 2 plus 3 minus, I to the 8th is also I to the 4th. So this is 3 minus 7. Minus 4 plus I to the 9th is the same as I. So I, or I to the 1st. So 8 minus 2 is 6. Plus 3 minus 7 is negative 4. And then let's distribute that negative minus 4 minus I. 6 minus 4 is 2. Minus 4 is negative 2. And then there's a minus I there. So negative 2 minus I. Okay, 4 more questions. Number sense. Write a pair of complex numbers whose sum is negative 4 and whose product is 53. Okay. 71. Sum equals negative 4. Product equals 53. I want to think on this. One thing that I know for sure is that if the sum is negative 4 for complex numbers, the i's have to cancel. So I'm going to need, in essence, a conjugate pair. Okay, so that works out. So I need a conjugate pair. I don't think anything will change with that except just to make sure that the real number thing isn't the part with the conjugate pair. It's the i's that are. So that's fine. And I already came up with an answer in my head, by the way. Because no matter what I do, the plus 3i minus 3i, the plus 8i minus 8i, as long as those cancel, I'm going to have a real number thing out. Oh, we do want a sum of negative 4, though, as well. I didn't come up with an answer for that. Let's see. Okay. Then I do have one here. Okay, so you need a conjugate pair. The real number needs to basically be doubled up on this. So a conjugate pair means with the sum being negative 4, we need the real part to be, right, if I double x, this is perfect. Doubling x is negative 4, my x needs to be negative 2 when it comes to, oh, how should I write this? 2x plus yi and 2x minus yi, kind of like that. No, let's see. How do I want to say it? Anyway, I need some sort of 2x plus yi kind of thing. I don't know how I'm saying this. I know what I want to do, but basically negative 2 needs to be the real part. It needs to be the real part because when I do my negative 2 plus this thing and negative 2 minus this thing, and I add those together, I need my negative 2 plus negative 2 to be negative 4. And I need then the i's to cancel out there. So the question is, I guess I can kind of put this within here now. Now I need a negative 2 plus bi times negative 2 minus bi. This was assuming you didn't guess and check, because my guess and check got me there. But we want this part to equal 53. Okay? We want this part to equal 53. Which means, and this is, so I'm going to work this out algebraically. When I do my stuff, this is negative 2 squared. So a squared plus b squared, right? Plus b squared equals 53. 2 squared, negative 2 squared is 4. So we will then subtract 4 and then take the square root of both sides, where we get plus or minus 7. So these are the two numbers that we get for the conjugate pair part. So I know I'm doing a lot of algebra stuff for that, but when they say write a pair of complex numbers, we need 2 plus 7i and 2 minus 7i. That is the answer pair that we need. We just saw how that kind of gets you 53. Excuse me, negative 2. That we saw how that kind of gets you 53. And you can see negative 2 plus negative 2 is negative 4. 7i minus 7i is 0. So that's what you get. I took up a lot of space for that one problem. And I kind of got the answer early on just by seeing 53 was 49 plus 4. But I had the order wrong. I forgot we had to add to negative 4, so I had to make the 2's negative. So there was a little more we had to do compared to the previous problems. All right, comparing methods. Describe the two different methods shown for writing the complex expression in standard form. Which method do you prefer, and explain? So let's see what they're doing. 72. Method 1. They are distributing. Oh, I see what they're doing. Okay, so on method 1, they do distribution. They turn I squareds to negative 1s and combine like terms. I prefer that one. Method 2, they are working out for basically 4i is a common factor of both of these quantities. It's a common factor, and then they combine like terms within to distribute afterward. You still get the same answer. This is an error analysis. It's just whatever. I prefer method number 1. If anything else, I mean, I understand method number 2. It's about a GCF thing. Method number 2 requires knowledge of GCFs within bigger quantities and without making mistakes. It takes longer. You can see more steps. It takes longer, and it requires the same. It requires the same factor. It requires the same factor to occur. Method number 1 is shorter and can apply to any general case. I can't see anyone who actually would prefer method number 2. It would have to be a very specific set of problems that all do the same thing for us to really find the quicker, more efficient method of that. Now, if you've done factoring by grouping, then you should know where method number 2 has this GCF thing of that 4i. That's totally fine. There might be forms for method number 2 being better. I can't see a lot of people arguing method number 2 being the preferred version there. Now, that's my own personal opinion. I'm sure everyone else will agree that just distribution, foiling, that kind of thing, whatever it is something that works out a little cleaner for us. All right, determine which, number 73, determine whether each statement is true or false. If it's true, give an example. If it's false, give a counterexample. Okay, the sum of two imaginary numbers is an imaginary number. When they say true, this is more so always, sometimes, never kind of thing. If it's sometimes, then that means it's not always true. So if it's not always true, then we say false. So the sum of two imaginary numbers is an imaginary number. False. I could have, we just saw one. We could see negative 2 plus 7i plus negative 2 minus 7i. This is an imaginary number. This is an imaginary number. The result is just negative 4. That the imaginaries canceled out. We got a real number as a result. So A is false. B, the product of two pure imaginary numbers is a real number. I can't think of a time when this is not true. This is true. For example, 3i times 6i is 18i squared, which is negative 18. Pure imaginary numbers. C, a pure imaginary number is an imaginary number. True. Example, true, but as an example, 2i equals 0 plus 2i. When it comes to imaginary, it says even with the real part, it still works out. D, a complex number is a real number. False. Every real number is a complex number. Not every complex number is a real number. So a complex number such as 1 minus 6i is not real. Okay. That was very open-ended for what you could say there. Number 74. Create a circuit. I don't even know how to draw that. Create a circuit that has an impedance of 14 minus 3i. I mean, I can do it. I just don't know how to draw it. So I'm going to copy. I thought I was out of the loop. No pun intended. Actually, I don't know if I intended that pun. That was really interesting. I just said that. I thought I was out of the loop on these circuits. Let's see if I can copy and paste just that one part. It won't be perfect, but I'm just going to draw one of those and work it out. Okay, let's see if I remember the terminology. All right, so here I have my, Here I have my inductor, and I have my resistor and my capacitor. My inductor is going to have some I component that'll be positive. So let's make one up, for example, here. Let's call it 5 ohms. If this is 5 ohms, that means I will have a 5i in my impedance, 5i. Now, my resistor has a resistance of, 14. I need 14 ohms for this guy because this is the only one that's going to stay real. So this will be the 14. And then I need my capacitor to have a reactance of something that gives me negative 3i as a result. So I'm going to call this 8 ohms compared to that 5 because then I'll have the minus 8i like that. So that'll give me 14 minus 3i. So this would be my answer to that guy right there with that drawing. I did it. There's my circuit. All right, guys, that ought to do it for this one. This is Mr. Robinson. I thank you so much for sticking around with me on this. Remember, the next section that we do on 4.7 is, I believe, solving quadratic equations where we have complex solutions. Just an I is just going to appear in some of the answers, whatever, but we're going to get those. We might do some rationalizing denominator. I have no idea. We'll see. But stay tuned for that one when it pops up. Thank you so much for watching, and take care. I will see you in that next one.